Greetings and welcome to the video introduction to the Chemistry 223 Exam 1 review, which covers chapters 12, 13, and 14 of our textbook. I'm really glad to have you here. In the normal Chemistry 223 lectures, for the exam review, I would present some problems. I would give students a few minutes to work on it, and then I would talk about the problem so they could see how they did, see how their knowledge was, see if it was up to speed and stuff like that. And in this video, I'm trying to emulate the same thing. I'm going to provide some questions, and then I'm going to ask you to pause the video and you can work on the problem, and when you're ready you can unpause the video and I'll talk about the answer. So it's kind of similar, and again, hopefully it gives you a chance to kind of see how you're doing with the material, if you're doing it right, stuff like that. At the time that I am creating this video, my plan for the first midterm in Chemistry 223 is that it will be over chapters 12, 13, and 14. So chapter 12 would be the thermodynamics, the delta G, delta S kind of stuff. Chapter 13 is equilibrium, and chapter 14 are acids and bases. So when you come to your midterm, I do encourage you to bring, of course, a calculator. That'll be helpful. Something to write with, i.e. a pencil would be cool. You'll bring the completed acid-base titration lab. You'll bring exam prep worksheet 1, which is a series of questions followed by the answer. You show your work, how to go from the question to the answer to get credit on it. And also bring a printed copy of that titration of weak acids lab. We will have a lab after the midterm, so just FYI, it's not a bad lab, but you want to bring that so you're ready to go. Now the midterm, as of the time of I'm creating this video, the midterm should have 12 multiple choice questions and 4 short answer questions, and it'll take about 90 minutes or so to complete. And then the next time I see you, probably the next lab period, I'll return the midterm to you with a summary sheet which says how you're doing in the class as of this time, and I encourage you to check it out. Make sure that the scores that are listed there are the scores you actually got. If you're missing a lab, make sure you turn it in, all that kind of stuff. The midterm will be closed note. You won't be able to have access to any notes or the book or anything like that. I will provide a periodic table to you. Don't bring your own. I'll provide one for you. Should be pretty chill. So without further ado, let's get into it. Again, if you have questions, reach out to me. I'm happy to help. But without more ado, let's get into the actual questions that will help you on the midterm. This question states, calculate the standard entropy change for the following reaction. This is a reaction where carbon tetrachloride reacts with oxygen to make CO2 and chlorine gas. And there are 4 entropy values listed right there. See if you can remember what we talked about in lecture to calculate the entropy change for this reaction. I recommend you pause the video, work on it, and when you're ready, you can unpause it. We'll talk about it. Pause the video now. Okay, at this point, I'm assuming you've had a chance to work on the problem and you want to talk about the answer. Let's do it. These kind of problems, all right, it's usually all of the products minus all of the reactants. This is an entropy problem, so you'd say it would be the entropy of the products minus the entropy of the reactants. And you can see all the values are given for you right there. So for this problem, what that means is you would take the CO2, which is the one product, and 2, by the way, times the chlorine, 2 because of the stoichiometry of 2 for the Cl. You would take those 2 together, those are the entropy of products, and you would subtract the entropy of the reactants, which in this problem is CCl4 and O2. So the 2 times the chlorine plus the CO2 minus the O2 minus the CCl4, and this is just something for your calculator. And when you do that, you get an entropy change 240.44 joules per Kelvin. This is an increase in the entropy. But just try and focus on the form. This is the official version of the equation. It's the entropy of the reaction equals the sum of, that's what that symbol means, the sum of all the entropies of products minus the sum of all the reactants entropy. And you just plug and chug the different numbers in. Make sure you multiply the chlorine by 2 because stoichiometries are affected. These entropy values are usually per 1 mole. Shouldn't be too bad. In this question, I want you to calculate the Gibbs free energy for this reaction, which is methane and oxygen making CO2 and water, okay? And there's some values for the Gibbs free energy and 5 possible answers. See if you can figure out which one of those answers makes the most sense. I recommend pausing the video. You can work on the question, and when you're ready, unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to try the problem and you want to talk about it, so let's do it. Okay, this kind of problem is similar to the last one we did with entropy, but this one now is about Gibbs free energy, delta G. But it's the same kind of process, Gibbs free energy of the products minus Gibbs free energy of the reactants. So for this problem, you would take the Gibbs free energy of the CO2 and 2 times the water, don't forget the stoichiometries, and you would subtract the Gibbs free energy of the reactants, the Gibbs free energy of the methane, plus 2 times the Gibbs free energy of the oxygen. But wait, there's no oxygen listed for Gibbs free energy. Wah! And about this time, you probably want to run around and go, that's it. I'm, going to go be a janitor or something. But don't you dare. We're almost to the end of Chem 223, so you hang on with me. But anyway, I digress. Notice here that oxygen was not included. Okay, and that's intentional. Oxygen is an element in its standard state. It's a gas. It's not a liquid or ozone or something like that. Elements in their standard states have delta G's equal to 0. This is the same for enthalpy delta H. If you have an element in its standard state, the delta G and the delta H value will be 0. For entropy, you'll always have positive numbers because the only time you have a 0 entropy is that perfect crystal at 0 Kelvin, which is never. So positive entropies are definitely going to happen for everything in a reaction. But when it comes to delta G products minus reactants or delta H products minus reactants, the elements will have a 0 value. So after this, it's just a thing to do in your calculator. Here's the same kind of thing. Delta G of the reaction equals the sum of the delta G's that are products minus the delta G's that are reactants. And again, you can see down here that oxygen is 0, so that's why it was not there. It's a good learning moment. Oh, those darn educators. Anyway, delta G, negative 800.8. Negative delta G's means spontaneous. This reaction will occur. This is the burning of methane, which is essentially natural gas. So all the times we've used Bunsen burners in the lab, or you've watched me use Bunsen burners if this is a virtual course, all the times that we have or might use Bunsen burners, you're going to have something happen. So delta G had better be a negative number. We should be able to burn methane, and we can. Oh, chemistry. Here's a reaction where magnesium is reacting with oxygen to make magnesium oxide. And given the information below, I'd like you to calculate delta G for this reaction. And delta H and delta S are listed. Okay, so use that information, see if you can figure out what the answer is. I recommend pausing the video. When you want to talk about the answer, unpause it and we'll talk about it. Pause the video now. Okay, at this point, I'm assuming that you've had a chance to work on the problem and you want to talk about the answer, so let's do it. This is a problem where you want to use what's called the Gibbs free energy equation. And the Gibbs free energy equation is delta G equals delta H minus T delta S, okay? And delta H is literally that delta H value that's listed right there. Delta S is the value of delta S listed there, and T is the temperature. Now, delta H is in kilojoules, and notice that delta S right now is in joules. You want to make sure that you're using joules and joules or kilojoules and kilojoules. And since all of the reasonable answers are given in kilojoules, I would convert delta S to kilojoules. You can do that easily by dividing by 1,000. You could use minus 0.10836 if you'd like, and that would be a kilojoules per mole value. The other thing, though, just to make sure everybody's clear, you want to make sure for temperatures you use Kelvin. So 25 Celsius plus 273 would give you a Kelvin temperature of 298 Kelvin. So after this, just plug and chug in the different numbers. Again, you can see there's delta S divided by 1,000. I used Kelvin temperatures, negative 568.9 kilojoules per mole of reaction, which means that's how much Gibbs free energy there is. This is a negative delta G, so that means spontaneous. This reaction will occur. And if you've ever seen magnesium burning in oxygen, it's incredibly bright, very, very bright reaction. This is an enthalpy-driven reaction. Enthalpy, when it has a negative number, is contributing towards the negative delta G. So negative delta H means enthalpy-driven. If this reaction were to be entropy-driven, you'd have to have a positive delta S. But this delta S is negative. negative. And that kind of makes sense because you're going from 1.5 moles of reactant to 1 mole of product. You're getting rid of a gas, which is always entropy favored. Entropy doesn't like this reaction. This is not an entropy-favored reaction. If it was a positive delta S, then you would have an entropy-favored reaction as well. So this one is enthalpy-driven, but not entropy-driven. We have a reaction which has a positive delta H and a positive delta S. And what can we say about the reaction spontaneity at different temperatures? Okay, before we get into the answers, we're going to go back. Delta G equals delta H minus T delta S. That's going to be the equation we want to use here. And if it's talking about reaction spontaneity, spontaneity means delta G. If it's spontaneous, delta G will be negative, okay? So you have 4 possible answers there. See if you can use this information to see which one is the best fit. I recommend pausing the video. You can think about it. When you're ready to hear what the answer is, unpause it. We'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on the problem. You want to hear the answer? Let's get into it. Positive delta H means endothermic, and a positive delta H makes delta G want to be positive, all right? Positive delta H makes positive delta G. This is not an enthalpy-driven reaction. If it's enthalpy-driven, you'd have a negative delta H. On the other hand, delta S, if it's positive, a positive times negative T, that's going to make that whole part right there negative. So a positive entropy does contribute to a spontaneous delta G, i.e. a negative delta G. This reaction is entropy favored. So this is an example where enthalpy and entropy are kind of fighting. Enthalpy does not want this reaction to occur. It's a positive delta H. On the other hand, entropy does want this reaction to occur. Positive delta S times negative T makes delta G want to be negative. So the two species are fighting. And when you have them fight, when they're both the same sign, then what's going to be the deciding part is literally the temperature. As temperature is higher, all right, it'll help the delta S term to win. On the other hand, if the temperature is lower, then that will make T delta S small, delta H will dominate. Small t helps make delta H win, if you will. So in this problem, delta S wants the reaction to go. High temperatures will make this reaction product favored, all right? Low temperatures will favor the delta H term, which will make the reaction less likely to occur. So positive delta H does not make reaction spontaneous, but positive delta S does support spontaneity. So when you have a higher temperature, negative T delta S will overpower delta H, making the reaction overall spontaneous, i.e. giving it a negative delta G. High and low temperature are very vague, all right? You can actually calculate what the temperatures are, and that threshold temperature, any temperature above would be considered high, and any temperature below would be low. But it does vary on the magnitude of delta H and delta S. Knowing at this point, without knowing the actual values, we can't say anything more. So high and low is just relative, all right? But it does kind of give you a sense. If you wanted this reaction to go, you'd want to pump up the temperature to try and make it overpower the delta H and make the reaction spontaneous. In this problem, we have a series of delta H and delta S values, and we want to calculate the delta G for this reaction, which is 2 hydrogen peroxides decomposing into 2 waters and an oxygen. And there's 4 reasonable answers and 1 silly answer there once again. Okay, in a problem like this, you want to find delta H, products minus reactants. You also want to find delta S, products minus reactants. Then you're going to combine your delta H and delta S into the Gibbs energy equation, delta H minus T delta S equals delta G, and that'll give you the answer. So try and work on this question by yourself. I recommend pausing the video. When you're ready to hear the answer, you can unpause it. We'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to dig into it, so let's do it. Like I said, this is kind of like a three-step process. First, you're going to find the delta H of the reaction. So that'll be delta H of the products, water and oxygen, and you'll subtract the delta H of the reactants, hydrogen peroxide, and you'll end up with some delta H of the reaction value. Then the second step is to do the same thing but for entropy. So you'll take the entropy of the products, water and oxygen, and subtract the entropy of the hydrogen peroxide, and that'll give you the delta S of the reaction. And then finally, delta G equals delta H minus T delta S. All right, make sure you turn the Celsius into Kelvin, make sure you turn the joules into kilojoules for entropy. I'm doing it because all the answers are in kilojoules, so it'll make it easier to understand. Not too bad. A little bit of math, but not too bad. So when you do that, I got out answer D. And let's break this down here, how we did it. So first step, find the delta H of the reaction, which is delta H products minus delta H reactants. There's no O2 delta H value listed. That's because elements in their standard states have delta H's equal to 0. This is similar to what we saw with the delta G values. Remember, delta G and delta H will be 0 for elements in their standard states. So delta H minus 196.0 kilojoules per mole. Now delta S, all the values will be positive, so you'll have to look up everything, including the elements in their standard states. So delta S products minus reactants, and make sure you include the stoichiometries of 2 in both delta H and delta S reactions. Delta S comes out to be positive 125.7 joules per mole Kelvin. Finally, you plug all of this into delta G. Delta G equals delta H minus T delta S. I do recommend that you turn the joules into kilojoules right there. So I divided by 1,000, 0.1257 would be the kilojoules. That way I have kilojoules and another kilojoules number. You don't want to use joules and kilojoules. That would mess everything up. Anyway, if you did it all right, minus 233.5 kilojoules per mole of reaction, answer D. You got this. This reaction is spontaneous, negative delta G. It is enthalpy favored because delta H is negative, and it's also entropy favored. Delta S is positive. So this reaction is going to go all the time, all temperatures. Delta H and delta S want this reaction to go. In this reaction, we have delta H negative 96.0 kilojoules per mole and delta S negative 12.6 joules per mole Kelvin. If the temperature is increased slowly, at what temperature will this reaction become non-spontaneous? And there's 5 possible answers there. One of them doesn't make any sense. But anyway, I want you to think about this question. This is when you're trying to find that threshold temperature when delta H and delta S are fighting. And notice here that delta H and delta S are both negative. If delta H and delta S have the same sign, that means they're going to fight. All right, that's kind of a weird way to think about it, but it's true. Anyway, see if you can figure this out. Pause the video. You can work on it. When you're ready to hear the answer, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on this question and you want to hear what the answer is, so let's do it. The Gibbs free energy equation, delta G equals delta H minus T delta S. When delta H is negative, it means it's enthalpy driven. This is an enthalpy driven reaction. But when delta S is negative, all right, delta S is not happy in this reaction. If delta S is positive, it's going to be entropy driven. This is not entropy driven. So they're fighting here. And delta S does not want this reaction to occur. Delta H does. So as temperature goes up, eventually delta S is going to be able to overpower delta H, and the reaction will become non-spontaneous, i.e. when temperature is large enough, the T delta S term compared to a delta H will make delta G a positive number. It will no longer be spontaneous. So in this question, what you want to do is you want to let delta G equals 0, because 0 is the threshold between being spontaneous and non-spontaneous. So delta H will equal T delta S, or T is going to equal delta H divided by delta S. And the temperature that pops out will first of all be in Kelvin. And second of all, that's going to be the threshold between spontaneity and non-spontaneity. Lower temperatures in this problem will be spontaneous. They'll give you negatives, but higher temperatures are the ones that are going to give you the non-spontaneous. Now, again, delta H is usually in kilojoules, delta S is usually in joules. So I would recommend converting the delta S to kilojoules, or if you want delta H to joules, doesn't really matter. Want to make sure you use the same kind of unit. But when you do that, and down here you can see that I turned delta S into a joules, or into kilojoules, excuse me. The temperature that pops out, 7,620. That's a Kelvin temperature, all right? And 7,620 Kelvin is the threshold between when a reaction goes from being spontaneous to non-spontaneous. Now remember that lower temperatures were spontaneous, so you can imagine that up to 7619 Kelvin, this reaction would be spontaneous. It would occur. But once you get just a little bit above this temperature, like 7621 Kelvin, then the reaction will be non-spontaneous, and it won't happen because above 7620, that's when delta S is able to overpower delta H when you multiply delta S by negative T. So this is kind of how these things work. You'd want to keep this temperature somewhat lower if you could, trying to stay away from this non-spontaneous threshold, but this is how you can calculate things like that using the values of delta H and delta S. Here's a question. Barium sulfite is poorly soluble in water. It has a KSP 8.0 times 10 to the minus 7th, again, much less than 1. What is delta G at 25 degrees Celsius? Again, 5 answers, 4 of them being potential answers. See if you can figure out what the answer is. Pause the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you had a chance to work on it. Let's figure out what the answer is. This question is converting a K into delta G. And what we talked about in lecture is that delta G equals minus RT natural log of K. And again, this is really sloppy. I'm really sorry. But delta G on the left side here equals negative RT natural log of K. K can be any kind of equilibrium constant, KSP, KA, KF, whatever. Okay, so you'd literally for the K, you'd put in 8.0 times 10 to the minus 7th. T is the Kelvin temperature, so 298 Kelvin. And R is the energy R, the 8.3145 number. One thing that will help is that K's less than 1 are reactant favored, and a delta G for a reactant favored condition will be a positive number. A negative delta G would be like a product favored, and that would be like a K greater than 1. So there's no way that the answer is going to be C. C, a negative delta G, would only come from a K larger than 1. So this is just one of those problems you got to plug the math in. You'll probably get joules per mole Kelvin out first, so you can divide by 1,000 to get kilojoules. Anyway, if you do that, you get 34,800 joules. Divide that by 1,000, 34.8 kilojoules per mole reaction. So again, K's less than 1 correspond to delta G's, which are positive, and that's kind of an important thing to remember. Just like if you had a K greater than 1, you would end up with a delta G, which was negative. First question, we place 0.010 moles of dinitrogen tetroxide in a 2-liter flask at 200 degrees Celsius. And after reaching equilibrium, the dinitrogen tetroxide concentration is 0.0038 moles per liter. Calculate Kc for the following reaction. And you can see that there's 5 possible answers down there. I encourage you at this point to pause the video and work on the question. And when you're ready, you can unpause the video and we'll talk about the answer. Pause the video now. At this point, I'm assuming that you've worked on the question and you want to think about the answer, so let's get into how you would solve this. This is the classic equilibrium kind of question, where you should set up the ICE table, and the equilibrium part of the ICE table will be the parts that you'll throw into the Kc expression. Now, the equilibrium constant expression, the Kc expression, for this reaction will be nitrogen dioxide squared in the numerator and dinitrogen tetroxide by itself in the denominator. But you do need the equilibrium values to answer this question. Another kind of hidden thing here is that when you're dealing with ice tables, you almost always want to use moles per liter. And you can see here that you have this many moles, 0.010 moles, in 2-liter flask. So the molarity will be initially 0.010 divided by 2. That will be the initial part of the N2O4. Make sure that you always use molarity in ice tables. So anyway, here's my ice table that I set up. Initial change and equilibrium is what ice stands for. And again, I did take the moles of N2O4 and I divided it by 2 to get this number right here, 0.0050. Technically, it should have another sig fig. Anyway, that's one of the part that sometimes is kind of confusing at first. We don't have any nitrogen dioxide. The change part will go down by X for N2O4, and it will increase by 2X for NO2. And because N2O4 is what we start with, it will decrease, hence the negative sign, and nitrogen dioxide has to increase. Remember, at equilibrium, you can't have 0 concentrations of anything. Also, because of the 2 on the 2 NO2s, that's why it's going up by 2X. So at equilibrium then, we'll have initially what is 0.0050 minus X, and NO2 would be 2X. But in this problem, it states that the N2O4 concentration at equilibrium, 0.0038 moles per liter. So the first thing you need to do in this one is solve for what X is. So you start with 0.0050 minus X equals 0.0038. And to solve for X, you would then take 0.0050 minus 0.0038. That would equal X. And X comes out to be 0.0012. And you need X to solve for NO2 because 2X is how much NO2 is going to be there at equilibrium. So 2 times 0.0012 is 0.0024. So Kc, 0.0024 squared, divided by the equilibrium amount of N2O4, which was 0.0038. That's how you get 1.5 times 10 to the minus 3. This is a reactant-favored equilibrium. K is much less than 1. The value E there, the negative number, is just in there for silliness. You can't have negative Ks. Ks will not be 0 or negative. They can be less than 1, absolutely, but not less than 0 or equal to 0 for that matter. So if you can do this kind of problem, you've got this stuff down. It's a little weird, I know, to see the 0.010 divided by 2, but it highlights the fact that you must use molarity almost all the time anyway in the ice tables. In this question, we're given 2 equilibria. The first is nickel 2 carbonate, and it's breaking down to nickel 2 plus and carbonate ions, and you can see the K value. The second reaction is hydrogen carbonate reacting with water to make carbonate and hydronium, and that expression is a Ka expression really, but I've just listed it here as K2, which is fine. K2 4.8 times 10 to the minus 11th. I'd like you to take those 2 equilibria and find the equilibrium constant for this reaction right here, which is nickel 2 carbonate plus hydronium, making nickel 2 plus hydrogen carbonate plus water. And one of those 5 answers there will be the right one. So at this point, I encourage you to pause the video, pause it and work on the problem. And when you think you've got a good answer, unpause it and we'll talk about what the answer actually is. Pause your video now. Okay, I'm going to assume you've had a chance to work on the video and you want to talk about the answer, so let me be the one to help you out with that. Woohoo! Anyway, if you need to combine equilibrium, all right, what I usually do is I try and look at the given equations and see how well they match up with the desired equation, kind of like what we used to do with Hess's law and stuff like that in Chem 221. Here's what I mean by that. In this first equation, nickel 2 carbonate is a reactant, and we want nickel 2 carbonate as a reactant. So I'm going to assume that we're not going to do anything to the first reaction, all right? Nickel 2 carbonate solid only appears on a reactant in the first one, and we want it as a reactant in the desired equation, so I think we're going to be okay. But if you look at the second reaction, hydronium is a product, and in the desired reaction, we want hydronium as a reactant. So we're probably going to want to flip the second equation around around, we're going to take carbonate and hydronium as reactants, and that will make hydrogen carbonate and water as products. So we're going to flip that reaction around. Now, when you flip an equilibrium expression, you take the inverse 1 over the old K value. So when we flip that around, we're going to go 1 over 4.8 times 10 to the minus 11th, whatever that is. That's going to give us the new equilibrium concentration. When we do combine those equations, we will multiply the K's together. We'll use 6.6 times 10 to the minus 9 as is, but we'll use basically 1 over 4.8 times 10 to the minus 11th for the second reaction. So here's what I did, all right? I used the first reaction as is, didn't touch it. Nickel carbonate goes to the ions, no problem. But I did flip the second reaction around, all right? Carbonate plus hydronium makes hydrogen carbonate and water. And if you combine these two together, all right, the carbonate on the reactant and the product side cancels. So the pieces that are left, nickel 2 carbonate plus hydronium, making nickel 2 plus hydrogen carbonate plus water, and that's exactly what we want in the desired reaction. So to figure out the net K, you take the first K as is, the 6.6 times 10 to the minus 9, but then you multiply by 1 over 4.8 times 10 to the minus 11th, or you can calculate that number, whatever it is. But you should get ideally to 2 sig figs a K net of 140. So this will be a product favored reaction. And what that tells you is that insoluble nickel 2 carbonate will dissolve in acid hydronium to make nickel 2 plus and hydrogen carbonate and water. Kind of a cool process. Here's a question. It's got a delta H, which is negative 18.8 kilojoules. It's got a Kc of 10.5, and there's the reaction, CH2Cl2 going to CH4 and CCl4. If the temperature on the equilibrium system is suddenly decreased, what's going to happen to K? Is it going to increase? Is it going to decrease? Or is it going to stay the same? Work on this problem on your own. I recommend pausing the video, and when you're ready to talk about the answer, you can unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've worked on the problem and you want to talk about the answer. Very, very cool. This question is a Le Chatelier's principle question. It doesn't say anything about Le Chatelier's principle, but that's what's happening. Temperature changes affect the values of K, okay? And what we're doing here is we have a reaction and we're suddenly cooling it down. The key for understanding this is to know what this part is all about. Now, delta H is enthalpy. The little zero means standard states. The enthalpy here has a negative number. That means this is exothermic. Heat is being generated in this reaction. And what I would do on problems like this is literally write in plus heat. Because if you do that, you can think about heat as a product, which I think makes more sense for Le Chatelier's principle. Now, if that delta H would have been a positive number, we would have written heat on the reactant side. But for this problem, we're going to write heat as a product. Now, in the question, you're suddenly decreasing the temperature. You're making it colder. And that's like moving or taking away heat from the system. And the system's going to get cold, all right? And if you go outside, you want to put a coat on if it's cold to keep you warm. Well, the reaction kind of tries to do the same thing here too. So if you cool this reaction down, that's like taking heat away. And the reaction's going to shift to make more heat. It's going to shift to the product side. And if it shifts to the product side, numerator is going to get bigger, denominator is going to get smaller, your K is going to go up. So again, I highly recommend that if you have this kind of Le Chatelier's question, you should actually write heat in. If delta H is negative, heat will be a product. If delta H is positive, heat will be a reactant. And then as you increase the temperature, that would be like adding heat. Or if you decrease the temperature, which is what we did here, it's like taking away heat. And remember, you take away something, the reaction's going to shift to the side that you're taking stuff away from. It's going to shift to the right, which means that K is going to increase, etc., etc. Here's a question. We're adding 0.535 grams of sodium hydroxide with a molar mass of 40.0 grams per mole to 100 milliliters of water at 25 degrees Celsius. What is the hydronium ion concentration in the solution? Just to make sure we're all clear, this little grams moles minus 1 means grams per mole. All right, that's just a notation that's sometimes used in science. This question is really about how to convert a hydroxide ion concentration to a hydronium concentration. So see if you can do this problem, all right? I recommend pausing the video. You can unpause it when you're ready to talk about the answer, and I'll go over it. Pause the video now. I'm going to assume you've had a chance to work on this. Let's get into the problem. We talked about in chapter 14, part 1, how all acids and bases are basically dictated and determined by Kw. Kw is the water autoionization constant. And at 25 degrees Celsius, which is where we're going to assume these problems are, hydronium times hydroxide equals Kw. And that value of Kw is 1.00 times 10 to the minus 14th. So if hydronium times hydroxide equals Kw, 10 to the minus 14th, we can use that 0.535 grams number to find the concentration of the hydroxide. So you can take 0.535 grams sodium hydroxide and divide by 40 grams per mole. That'll give you the moles of sodium hydroxide. Divide by 0.1 liters, which is 1,000 milliliters per liter if you turn 100 milliliters into liters. Moles divided by liters will give you the molarity of hydroxide, and then Kw divided by whatever number that is going to give you hydronium. You must know Kw, all right? It's just a number we're going to use over and over and over and over again. You must know what Kw is, okay? But anyway, if you do all those steps, the answer comes out to be 7.48 times 10 to the minus 14th. Here's the way that I calculated hydroxide: 0.535 grams divided by the 40 grams per mole. 1,000 milliliters per liter means that 100 milliliters would be 0.100 liters. So the concentration there, to way too many sig figs, but that's not what we're stopping at, is that number. Kw divided by that number, 7.48 times 10 to the minus 14th moles per liter. Very, very, very small amount of hydronium. As hydroxide goes up, hydronium goes down. And even though that doesn't look like a lot, 0.535 grams, in the chemical world, that's actually quite a bit, all right? And so that relatively high amount of hydroxide pushes hydronium way down, no problem. If you consider only the H2S and HCN equilibrium, and there's two Ka values right there, predict in which direction the following equilibrium lies. And this reaction is hydrocyanic acid reacting with hydrogen sulfide to make cyanide and H2S, which is hydrosulfuric acid. Anyway, the answers: equilibrium lies to the left, reactant side; equilibrium lies to the right, product side. It's perfectly balanced between left and right, or it cannot be determined. So try this problem, all right? See if you can play with those Kas. You got to know what a Ka means to answer this question. See if you can figure out what the answer is. I recommend pausing the video. When you're ready, you can unpause it. We'll talk about the answer. Pause the video now. Okay, I'm assuming that you've worked on this question a little bit. You want to talk about the answer, so let's get into it. This question really revolves around what a Ka is. And remember, Ka is an acid dissociation equilibrium constant. Kas are used extensively for weak acids. If K is less than 1, it means you have reactant-favored conditions, and both of these Ks are definitely less than 1. Now, there's a couple different ways to do it, but I'm going to show you what I think is the best way, all right? But it's not necessarily the only way. One way to do this would be to literally combine Ka expressions, all right? You would combine the Ka for H2S, and you'll end up using the Ka for HCN. But you have to be careful here. The reaction has HCN as a reactant, and H2S, the other acid, is a product. So what I would do here is I would write HCN, and if it's a Ka expression, HCN reacts with water. It makes the conjugate base, which would be cyanide, and hydronium. And that Ka expression there would be 4e minus 10. I can't write on this thing very well, so sorry, it's pretty cheesy, but hopefully you get the idea. I'm doing that because HCN is a reactant, and I want HCN as a reactant if it's a Ka, so this is really good. However, H2S, we want it as a product, all right? And H2S is not normally a product in a Ka. So I need to reverse the Ka expression for H2S. So what that means is I would have H2S and water as products now because I'm reversing it. And then the conjugate base, which is HS minus, and hydronium would be my reactants. And the K here would be 1 over the K for H2S, so 1 over 1E minus 7. All right, pretty funky. At this point, you could combine equilibrium. And so, for example, the hydroniums will cancel, the waters will cancel, and you can see that what's left, you've got HCN and HS minus, which is what we want as reactants, and cyanide and H2S would be the products, and that's what we want. And then to figure out K here, you'd get 4e minus 10 times 1 over 1 times 10 to the minus 7th. That would give you an equilibrium constant. I think you're going to see that it's reactant favored, which means shift to the left. That would be probably the ultimate way to do this problem. I won't lie. However, there is another way to do this problem, and it has to do with the strengths of acids. Acid strength always goes from strong to weak, all right? And if you look at this desired reaction, we have two acids, HCN and H2S, all right? The stronger acid is going to push towards the weaker acid. And strengths of acids, we can use literally the Kas. H2S has a lot bigger Ka. 10 to the minus 7 is small, but it's a lot bigger than 4 times 10 to the minus 10. So 10 to the minus 7 is going to push this reaction to the reactant side. And I didn't need to write out Ka expressions or anything like that. I literally just looked at the values of Ka. Bigger Ka is going to push to the smaller Ka. HCN has a smaller Ka. It's going to be on the left. So regardless of which way you do it, all right, this reaction is definitely going to be reactant favored. It's going to be pushed towards the left, all right? And you can actually figure out the equilibrium constant K by multiplying these two together. You'll get a number less than 1, which means reactant favored. Or you can literally just look at the strengths of Ka, and bigger Ka will push towards the smaller Ka. Down here I have a little advertisement. You could also do this with Kb's, and I didn't give you those in this problem, but you could also look at the Kb values. Bigger Kb is going to push to smaller Kb. Cyanide has a bigger Kb, 10 to the minus 5, than HS minus, which is 10 to the minus 7. So that's another way that you could also show this reactant is going to be reactant favored. Oh joy. In this question, we want to find the hydronium of a 0.10 molar hydrocyanic solution at 25 degrees Celsius, and the Ka for hydrocyanic acid, 4.0 times 10 to the minus 10th. All right, I recommend you work on this problem. Pause the video. You can work on the problem, and when you're ready to talk about the answer, you can unpause the video and we'll talk about it. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so let's do it. Weak acids, all right, don't contribute all of their moles to hydronium. We've seen that for Ka expressions, you take the acid and you add water to it on the reactant side, and the products will be hydronium and the conjugate base. So for this reaction, that would be HCN plus water, and it's in equilibrium with the conjugate base, which is cyanide, plus hydronium. And the question is, how do we get hydronium out of this equilibrium expression? And one way to do this was you could do the ICE table. All right, you're starting with 0.10 moles per liter of HCN and 0 cyanide and hydronium. Water is a liquid, so you don't need to worry about that. HCN will go down by X, cyanide and hydronium will go up by X, so you'll end up with X squared over 0.10 minus X equals Ka, 4.0 times 10 to the minus 10th. You can solve the quadratic formula, get an X value, and that X value will be hydronium. Totally fine. However, you can also make it a lot easier on yourself because 0.10 minus X is basically going to be equal to 0.10. We talked about in lecture how if 100 times K is less than C, you can totally do that. And 100 times Ka, 4.0 times 10 to the minus 10th, is 4.0 times 10 to the minus 8th. And that's a heck of a lot smaller than 0.10. So knowing that then, you can ignore that minus X by the 0.1, and hydronium will equal square root Ka times Ca. Another way you could do this is you could use one of my beloved short, quick, and dirty expressions for a weak acid. pH equals minus log square root Ka times Ca. You could solve for pH and then go 10 raised to the power of minus pH to get hydronium, or again, you could just do square root Ka times Ca. Totally up to you. But if you did all these problems, you should get answer B. Now you can see what I did is I used my beloved short, quick, and dirty expression, pH minus log square root Ka times Ca, and we will use that a lot. The pH comes out to be 5.20. You can check yourself. It is acidic. That's good. HCN is an acid, although not a very strong one. And then 10 raised to the power of minus 5.20 gives you 6.3 times 10 to the minus 6. Again, you could just use square root Ka times Ca to find the value. That would be fine too. And you could even use the quadratic formula. 4.0 times 10 to the minus 10th equals X squared divided by 0.10 minus X. Use that solve button. Your call. But hopefully at the end of the day, we'll all end up with the same answer. Life is good. In a 0.15 molar solution of sodium carbonate, what are the hydronium, the hydroxide, and pH values? And there's a Kb for carbonate. It's 2.1 times 10 to the minus 4. All right, I would recommend working on this problem, see how far you get. You can pause the video, and after you've worked on it, you can unpause the video, and we'll talk about the answers. Pause the video now. Okay, I'm assuming you had a chance to work on the problem and you want to talk about the answers, so let's get into it. First of all, what the heck kind of chemical system do we have here? That might be a question you're asking. And it's a pretty easy question to answer because you have a Kb. Kb stands for base. So carbonate, the sodium carbonate, that's a base, all right? It's going to affect the pH. pH should become more basic, all right? The Kb value there, 2.1 times 10 to the minus 4, isn't the smallest one. However, 100 times Kb would be 2.1 times 10 to the minus 2, and that number is less than 0.15 the Cb. So like we did in the last problem, if you'd like, all right, the hydroxide ion concentration is going to equal square root Kb times Cb, and that's how you could find the hydroxide value there. You could also use the quadratic formula if you'd like, but that would, whatever, that's cool. Anyway, once you have hydroxide, all right, there's a couple things you could do. You could find hydronium. Hydronium equals Kw divided by hydroxide. And once you have hydronium, minus log of hydronium will give you the pH. And if you did all those steps, that's fantastic. And that's a really cool way to do it. But let's think a little bit more about what it means to be a base, and this is a basic solution. If you look on the far right column, there's 4 possible answers, but they repeat, like there's 2 5.61s and 2 11.75s. If this is a base, the pH is going to have to be greater than 7. There's no way that answer A or answer D is going to fly, because a base has to have a pH larger than 7. So we're automatically going to disqualify A and D here. Those would be acidic pHs. That's not going to work. Now, you can even go farther than this. If it's a base, your hydroxide concentration should be a bigger number than your hydronium concentration. So if you look at B and C, B has a smaller hydronium than the hydroxide. 10 to the minus 12 is certainly smaller than 10 to the minus 3. C has a larger hydronium than it has hydroxide. C, if it has more hydronium, that means you're going to have an acid. You're not going to have a base if you have more hydronium than you have hydroxide. So by default, you can say answer B. Here's the actual work you can do to do this, and that's probably the better way. All right, and you can see what I did in this problem is I used one of my beloved quick and dirty expressions, the pH of a weak base, which is 14 plus log square root Kb times Cb. You are justified in using that because 100 times K is less than C. That's where the 11.75 came from. Then hydronium equals 10 raised to the power of minus 11.75. That's where the 1.8 times 10 minus 12 number came from. And hydroxide equals Kw divided by hydronium. That would be 5.6 times 10 to the minus 3. Again, you could have found hydroxide first. Hydroxide would be square root Kb times Cb and worked your way to hydronium and pH. There's many different ways to do it. But again, sometimes if you just think about these problems, we automatically kicked out the other 3 answers. They didn't make sense. If it's a base, you must have a basic pH. And if it's a base, your hydroxide needs to be a bigger value than your hydronium. Right? That's what a base is. So there's a couple different ways to solve it. Any of these ways are awesome. Cool. Here are 4 acids with 4 pKa's, and I'd like you to put them in order of increasing acid strength. Now remember, pKa is related to Ka, and Ka is related to the strength of the acid. So think about those 4 values right there and put them in order of increasing strength, weakest to strongest. All right? Pause the video, work on this question, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've had a chance to work on the problem. You want to talk about the answer, so let's get into it. These are pKa's. They are not Ka's. If they were Ka's, then the biggest Ka would be the most acidic, all right, has the most hydronium, and the smallest Ka would be the least acidic. But this is a px scale, and for pH, which is hopefully the most familiar to you, smaller numbers mean more acid, and bigger numbers mean less acid. So because these are pKa's, the strongest acid here will have the smallest pKa. 2.98 should be the smallest one. The biggest pKa will be the weakest acid. So of these problems right here, you want to go from biggest pKa to smallest pKa. And I believe that's going to be D, A, B, C. I believe the answer here is D. Now, if you can see pKa versus acid strength, that's the best way to do this, all right? And just like pH goes down, acid goes up. Well, pKa goes down, acid goes up as well, because Ka is related to the strength of the acid. But if you don't know, there's nothing wrong with converting these pKa's into Ka's. So you could go 10 to the minus 4.60 to get the Ka for the aniline ion there and answer A. You could go 10 to the minus 3.09 power to get the Ka for that one, etc., etc. And from there, you could go smallest Ka to biggest Ka for smallest acid to strongest acid. So either way you do this is cool. It does help. There's a trend in organic chemistry, I feel, that talks about acids more in terms of pKa than anything else. So knowing this trend can be helpful in later classes. We have a solution of ammonium chloride. What effect will happen if we add ammonia to the pH? So the pH will be affected probably by the ammonia. what will be the effect? It can increase the pH, it can have no effect on the pH, or it can decrease the pH. Or maybe we can't tell. See if you can answer this question. I recommend pausing the video. You can think about it a little bit. When you're ready to hear the answer, unpause the video. We'll talk about the answer. Pause your video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so let's get into it. Okay, on questions like this, you basically ignore what was already there because we just want the effect upon adding, in this case, ammonia. So you only need to think about what the effect of what you're adding will be. And in this case, NH3, as we've seen, is a base. It's a weak base, it's a Lewis base, all that kind of stuff. It's a base. And anytime you add a base, it's going to make your pH become more basic. It's going to increase the pH. We don't know how much it's going to increase the pH, maybe just 0.000001 units, or maybe, 2 units, who knows? But we know it's a base. Bases increase the pH, and that's the end of this problem. That's literally it. If we would have added an acid, it would have decreased the pH, and there are some compounds that don't affect pH too, but ammonia definitely going to increase the pH. We have a solution of ammonium chloride. What effect will the addition of NaCl have on the pH of the solution? And like before, maybe it's going to increase the pH, maybe have no effect, maybe decrease the pH, or maybe we can't tell. So try this problem. I recommend pausing the video. When you're done thinking about it, you can unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm assuming you had a chance to work on this question and you want to talk about the answer, so let's get into it. Like the last problem, you can ignore the ammonium chloride, all right, because we don't care what's going on there. We just want to know what the effect will be upon adding NaCl to the solution, all right? Well, NaCl, you have to think about the ions, all right? So for example, if it was ammonium chloride, ammonium is the conjugate acid of ammonia. So if we were adding ammonium, that was adding an acid, it would decrease the pH, become more acidic. Chloride, on the other hand, chloride is the conjugate of hydrochloric acid, and conjugates of strong acids and strong bases don't affect pH. So chloride, in both ammonium chloride and sodium chloride, chloride has no effect on the pH. Chloride, you can think about it as being the conjugate base of hydrochloric acid. Sodium ions can be considered the conjugates of sodium hydroxide, a strong base. And all conjugates of strong acids and strong bases do not affect pH. So sodium chloride will have absolutely no effect on the pH of the solution. And we know that because sodium is the conjugate of sodium hydroxide, chloride is the conjugate of HCl. And both of those are very, very strong. They push the equilibrium back to the original ions. They have no effect on the pH. So that's kind of a cool way to see what's going on. Here are 5 possibilities for a buffer solution. Which one of those would be an ideal buffer solution? Think about what makes a good buffer to answer this question. Okay, I recommend pausing the video. You can think about this problem, work on it, and when you're ready, unpause the video. We'll talk about the answer. Pause the video now. Okay, I'm assuming you've had a chance to work on this problem and you want to talk about the answer, so let's get into it. In a buffer system, you must have 2 requirements. First of all, the buffers have to have only weak acids and weak bases, no strong acids or strong bases. Strong acids and strong bases push the equilibrium too hard, so they don't coexist well with each other. The other thing you have to have, though, is you have to have conjugates. You have to have an acid with its conjugate base or a base with its conjugate acid. So as I look through these questions, I see a lot of strong bases and strong acids. Sodium hydroxide is a strong base, HCl is a strong acid, KOH is a strong base, HCl is a strong acid. So right away, answers B, D, and E are kicked out, all right? None of those are going to work because they have a strong acid and or a strong base. So we're down to A and C. And remember that you have to have conjugates of each other. And conjugates are just two chemical systems related by plus or minus a hydrogen. Well, if you look at C, you've got essentially acetic acid, and this thing right here is formic acid, which you don't need to know. But if you look there, for example, there's extra hydrogens and carbons in the acid relative to HCO2H. Those two are not conjugates of each other. First of all, they're both acids, which is a no-no in these kind of things. You have to have conjugates of each other, so C isn't going to play. Now, A at first maybe doesn't look like conjugates, but remember potassium of potassium cyanide. Potassium is a spectator ion, and in solution it will drop away. K plus is the conjugate of KOH, so it won't affect your pH. And as K plus goes away, you're going to have cyanide. So cyanide plus H plus makes hydrocyanic acid, HCN, and HCN minus H plus makes cyanide. So the answer here is definitely A. Those are the conjugates of each other. Don't have any strong acids and strong bases in your buffer. The two systems must be conjugates. They can't both be weak acids, which is what ended up happening there on C. Pretty crazy. But this is a good way to then pick out which one of those would be the best buffer system. So here's another buffer question. What would be the pH of a buffer that has 0.20 molar ammonium chloride and 0.20 molar ammonia? And it gives the Ka for ammonium there, 5.6 times 10 to the minus 10th. There are a couple different ways to solve this problem. I would recommend using the Henderson-Hasselbalch equation because I'm in love with that equation, let's be honest, if you've watched the lectures. But anyway, it's a very quick way to find the pH of a buffer system. So I recommend that you pause the video, work on this a little bit, and when you're ready to talk about the answer, you can unpause the video, pause the video now. I'm assuming you've worked on the problem, you want to talk about the answer, so let's do this problem. Okay, like I said earlier, there are a couple different ways you could do this problem. You could set this up as an ice table, all right? You'd have ammonium chloride plus water basically making ammonia and hydronium and chloride, and you pull the chloride out. You have both ammonium and ammonia. Ammonium will go down because you have to make some hydronium, so ammonia and hydronium would both increase by X. At equilibrium, you'd have 0.20 minus X for ammonium, and ammonia would be 0.20 plus X, and hydronium would be X. You'd set that all equal to 5.6 times 10 to the minus 10th. You could go through quadratic. You could pull out the plus X and minus X like we talked about in lecture, etc., etc. However, I highly recommend you start thinking about the good old Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, pH equals pKa plus log, and it's base over acid. And again, I can't draw very well in this thing, so bear with my bad handwriting. pH equals pKa plus log base over acid. Now, pKa comes from Ka, so minus log of 5.6 times 10 to the minus 10th, that's going to give you the pKa. Now, base over acid. Base over acid can be moles per liter over moles per liter. It can also be moles over moles. In this problem, it makes sense to have moles per liter over moles per liter. So 0.20 divided by 0.20. Notice that it is log of 0.20 divided by 0.20 or log of 1. Log of 1 in your calculator is 0. So in this problem, pH is going to equal pKa. So when you figure this problem out, 9.25. If the base and acid concentration, i.e. the ammonia and the ammonium, are the same, then pH equals pKa. So minus log of 5.6 times 10 to the minus 10th is 9.25. That's how you're going to find pH here. This question is similar to the last question, but now you do have unequal quantities of ammonium and ammonia. So this question is similar to the last one. We want to find the pH of this buffer. However, now we have ammonium at 0.20 moles per liter and ammonia of 0.950 moles per liter. Remembering that pH equals pKa plus log base over acid, I would use the Henderson-Hasselbalch equation. The base is is ammonia, the acid is ammonium, all right? And from there, you can find what the answer is going to be. So I recommend you pause the video, work on this question a little bit, and when you're ready to talk about the answer, unpause the video and we'll see what's going on. Pause the video now. Okay, I'm assuming you've worked on the problem, you want to talk about the answer, so let's do it. So again, what I would recommend for this question is the same as the last one. pH equals pKa plus log base over acid, okay? And the base here will be ammonia, and the acid will be ammonium. So you'd have log of 0.50 divided by 0.20. You can use the same pKa from last time, etc., etc. Anyway, if you do all this problem out, then you end up with a pH of 9.65. And at first it might seem kind of weird, some of these numbers, but the last problem, pH was 9.25 when the ammonium and the ammonia were equal concentrations. And notice in this problem, we have more ammonia, more base, okay? So our pH should be more basic than it was last time. It should be more basic than 9.25, and it is. So that's some ways that kind of make me feel better about problems like this. You have a more basic pH because you have more base than you had before. So that's kind of a cool thing. In this question, we want to find what volume of 0.10 molar sodium acetate must be added to 100 milliliters of 0.10 molar acetic acid to have a pH of 4.00. Okay, again, this is a problem where there's multiple ways to kind of solve this kind of thing. Again, I would probably recommend using Henderson-Hasselbalch, but again, that's just kind of my way. Anyway, I do recommend that you pause the video, work on the question a little bit. When you get an answer, you can unpause the video. We'll talk about the answer. Pause the video now. I'm assuming that you've worked on the question and you want to talk about the answer, so let's get into it. I'm a big Henderson-Hasselbalch fan, as I've told you multiple times already. So for this problem, what I would do is I would start with the mole version of the Henderson-Hasselbalch, and that's pH equals pKa, just as before. But in the previous problems, we use moles per liter over moles per liter. In this problem, I'm going to use moles over moles, and that's something you can do with HH. So instead of base over acid in molarity, now we're going to have moles of base divided by moles of acid. And you're probably like, well, that doesn't seem any better. And I totally understand. Moles, all right, moles equal the concentration, molarity, times the volume, all right? So instead of writing moles of base, you can also write the concentration of the base times the volume of the base. And for moles of acid, you can write concentration of acid times the volume of acid. Okay, now if you look at this question, all right, I'm going to use different colors. You have the pH 4.00, and that's what goes right there. You can turn 1.8 times 10 to the minus 5 into pKa minus log of that number, and that's going to give you pKa. Volume times concentration of acetic acid, all right, that's this part right there. And if you want, you can even use 100 milliliters. That's totally fine, because the top part, if it's in milliliters too, you'll be okay. And the base, which is the acetate, that's concentration of the base. So if you look carefully, the only thing you don't have then is volume of base. So pH 4.00 equals pKa, whatever minus log 1.8 times 10 to the minus 5 is, plus log, and in numerator, 0.10 times x, which is going to be the volume of your base, and in the denominator, 0.10 times 100 milliliters. And you can literally go through them and solve for the volume of the missing base. So let's see what the math looks like. What I did here is I first solved for the pKa, and minus log of 1.8 times 10 to the minus 5 is 4.74. And that's the number that we're going to put in here in a little bit. Now, Acetate is the base and acetic acid is the acid, all right? So base over acid means acetate divided by acetic acid. And you can see what I did. I went concentration times the volume, and we don't know the volume of the acetate, VACE, all right? But we do know the volume and concentration of the acid, all right? And I actually went through and solved that in this version of the problem, which is cool. So then Henderson-Hasselbalch, pH equals pKa plus log base over acid. Well, here's the pH here's the pKa we calculated, plus log base over acid. Here's the concentration times the volume, and here's the moles of the acid in the bottom. So I'm basically trying to solve for the volume of the acid. So the first thing you do is you go 4.00 minus 4.74, and that comes out to be minus 0.74, and that equals log 0.10 times V divided by 0.010. Then you can do the anti-log, and base 10 log is 10 to the x. So that gets rid of the log on the right side. Then you go 10 to the power of minus 0.74 on the left. And this is just fun for your calculator, okay? 10 to the minus 0.74 is 0.182. And that equals 0.10 times V divided by 0.010. You want to solve for the volume of the acetate. So 0.182 times 0.01 divided by 0.10 comes out to be this number, 0.0182 liters. Because I used liters up with the acid, my answer came out with liters. If you use milliliters, you'll get the milliliters right away. Anyway, 2 sig figs, 18 milliliters. This is kind of a cool little handy thing sometimes with buffers. If you just want to know the volume to add to make the buffer, this is neat. You have to know that moles equals concentration times volume, but once you do that, plug and chug, you're good to go. Here's a graph, and it represents one of the types of titration that we looked at in the lab. And I'd like you to tell me which of those 5 combinations it could be. So again, if you need to, pause the video, think about this question, and when you're ready to think about the answer, unpause the video, we'll talk about it. Pause the video now. Okay, I'm assuming you worked on the problem. You want to talk about the answers, so let's get into it. Okay, so first of all, the pH is the y-axis, and you can see that it goes from 0 to 14 supposedly, while the volume of the titrant there goes from 0 to 40. Now, when I look at a graph like that, first of all, I want to see where the pH is starting. And this pH is starting at a pH greater than 7. That means basic, all right? And in the types of titrations we looked for, what you start with is always listed first. So it will not be a strong acid, strong base. Strong acid, strong base would start out acidic. It also won't be a weak acid, strong base, because even weak acids would start acidic, not basic, okay? So we already eliminated A and C. Let's think about now what else is going on. After I figure out what you start with, the next thing I look at is where is the equivalence point pH of the titration. And that's what that little dot right there is. It's the middle part of the steepest part of the titration, if you will. And that equivalence point pH will be a hint. And if you go over on your y-axis, all right, whatever pH it is, it's certainly less than 7. Now, a strong base plus strong acid titration would have an equivalence point at 7. And this one is certainly less than 7, so this isn't a strong base plus strong acid titration. Now for the remaining 2 types, all right, we did not look at weak base plus weak acid titrations. That's a whole nother ball game. You have to think about Kas. They're kind of unwieldy and they're not used very much, to be honest. So don't even think that's a possibility. The only one here that fits is the weak base plus strong acid. And again, what I did, you can see I even highlighted it there. I looked at that equivalence point pH. It's basic. I looked at that equivalence point pH and it's acidic, all right, it's less than 7, okay? So that means that, yep, all of the weak base has turned into its conjugate acid. So at equivalence, when the moles are equal to each other, you do have an acidic pH, no problem. Okay, that completes the video introduction to the first midterm of Chemistry 223, and I hope this has been helpful. If you found that there were some places you could need some, you might need some more practice on to kind of booster your knowledge before the actual midterm, I encourage you to check out things like the practice problem sets, the concept guides, and chapter guides. You can also check out the end of chapter problems in our own textbook, because basically every other answer is given in the back, so you can try the question, and if you get it right, checking yourself at the end, you're good to go. So all those things should help. I wish you the very best on this midterm, and again, I hope this has been helpful. Thanks for spending your time with me, and have a great day.